I'd like to make a little video about the next section we'll cover, section 3.3, which is rates of change. We've already talked a little bit about this with functions, but here's a formal definition of a rate of change. So rate of change describes how the output of the quantity changes relative to the change of the input quantity. The units are going to be always per. Output units per input units. And we've talked about this. We've talked about examples where it's f of x2 minus f of x1 over x2 minus x1. That's better known as the rise over the run, or the slope. And this delta of x over delta of y equals delta y, which is a change in y. And delta x is the change in x. So what that represents is just the change in the y values over the change in the x values, and that's the rise over the run, and that's the slope. And so if we have these 2 points here on the function, we can approximate that curve by a straight line between those 2 points and find the slope between those 2 points. And we're going to get the rise here and the run here. Okay. And what we've done in class is we've had, it doesn't have to be x1 and x2. It could be x and a, like in this example. And so the first point here would have the coordinates f of x, and the point up at the top would have the coordinates a, f of a. And so we did some examples where you plug in x or a or anything into that function and you get f of a in this case. And with that notation between the points x and a, what's the rate of change? Well, it's going to be the rise, which is going to be f of x, or f of a minus f of x over a minus x. And notice it's the same as f of x minus f of a over x minus a. Multiply the top and bottom by negative 1 over 1, or sorry, negative 1 over negative 1. So it's a little fact that it doesn't matter which point you put first or second, which order you place them in, as long as you're consistent and you have the f of the first minus f of the second over the first minus the second, then you'll get the same rate. It doesn't matter which one you label as x or which one is labeled as a. And so we've done some examples where we've had to simplify an expression like that for some basic formulas. As an example in the class, we have things like this, where you have f of x is some function of x. And we want to look at the interval where x equals 2. So let's say x1 equals 2 and x2 equals 4. Then the rate of change is going to be f of x2 minus f of x1 over x2 minus x1. And then all we do then is plug in the values that we're supposed to for the rule and see how that works. So the rule is squared minus 1 over the value. And then we've got minus something squared minus 1 over the value. And the important thing is to put them in parentheses, each part. And that's because since you're subtracting, that will remind you to distribute the negative sign as you go. So this distributes through there when we get to it. And then we divide by, so in this case, we plug in 4 and 4, and then we'll do 4 minus. And then let's pick a different color, and we'll plug in 2 and 2 and 2. And so then it's just a matter of simplifying that expression. Equals whatever. I don't want to take the time now to calculate that all out. You plug it into your calculator, you simplify the fractions, and you get a number. And that number will be the slope of the curve between those 2 points. So I want to show you how you can see this on a graph. So let me open up Desmos. So I did this on Desmos, and I've typed in the function y equals x squared minus 1 over x, and that's the blue function here. And I've selected the point 2, f of 2, and 4, f of 4, and we can look to find what the slope is between those. And so that slope is going to be the rise over the run. And that's exactly the value that we had up above. We can plug that in. So here I've graphed x squared minus 1 over x in Desmos, and it's the blue function. It has two parts, this U-shaped thing on the left and then the squiggly thing that comes up from the bottom off to the right. But between the point 2, between 2 and 4, you can find that red line is the slope between those 2 points. There's the line between those 2 points. And what's the slope of that? Well, it's f of the top point minus f of the bottom point over the difference in the x values. And that's written over here in the formula that we've had in class, f of b minus f of a over b minus a. That's exactly what's going to be the change of the y values divided by the change of the x values. And in this case, it'll calculate it for you on Desmos, and it's 6.125, which is the answer that we got when we said whatever earlier. And the cool thing about calculus is we can do some algebra and simplify this and actually get an expression for it. And as b gets closer and closer to a, what happens when it's really close to a? The blue curve is curving. It doesn't have a straight line. It doesn't have a straight tangent. But as you zoom in, we can figure out the slope of that blue line is really, really almost identical to the slope of the line between those 2 points. The more you zoom in and the closer your 2 points get, it's indistinguishable, the curve and the straight line. So that means you can define the slope of that curve at that point to be 4.3 in this case. And as you get closer and closer, actually it's probably getting down to 4.25. I'll bet it's, and as you zoom in, that slope gets closer and closer to some limit, and you can say that the slope at that point is 4.25. And in calculus, you figure out formulas to find functions that give you the slopes at these points. And all these calculations we've been doing, you can do almost in your head for some of these. I mentioned that in calculus, you learn formulas and rules to find this derivative formula, this slope equation. If I give you a function for f of x, for in this case, we have f of x equals x squared minus 1 over x. You learn a few rules that pretty quickly you can calculate that this slope function called the derivative function, which I've labeled as g of x equals 2x plus 1 over x squared. And what that allows you to do is, as we showed, when you slide the other variable, other point in, so these are really close together, even closer, 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 the slope formula down here is 4.3. When I zoom them even in closer, they approach 4.27, 4.2, and it's 4.25, which is the value of this derivative function g when I plug in a equals 2, 4.25. What happens if we zoom out and now pick a different point? Let's say we try a equals up here at 3, and I'm going to drag the a, both a and b really close to 3. And when I zoom in on that, what are the slopes? Well, the slopes are about 6.17. I look a little bit closer, 6.12, 6.13. And if I make a exactly 3, the slope at a is exactly the same thing. I can't quite make it exactly 3. So the slope at 3 by the formula is 6.12. By our estimation is 6.16. So you can zoom in and they'll actually become exact if you zoom in closer and closer. And so that formula is a nice little formula. You just plug in a equals 3 into that and you get the slope. What about, let's do one more. What if we drag a down to be around 1? In that case, you can see it tells us exactly what the slope is. The slope, if I plug in 1 for this g of x formula, I get 3. And if I plug in these 2 points that are really, really close together, I also get really, really close to 3. And so this formula is this magic little formula that is not too hard to figure out once you know a few rules, and it tells you what the slopes are going to get really, really close to at and nearby 3. Or sorry, in this case, a equals 1, and the slope will be 3. That's really nice. So I wanted to do an example similar to one that we've talked about in class, where we have this g of a minus g of 0 over a minus 0 form that we've talked about, where it was g of x minus g of a over x minus a in a couple examples before. But those values just determine a couple points that you've got. And so if we want to find between 0, comma 1 and a, comma g of a, we want to find the slope of that line, and that will approximate the slope of the curve in that point if they're close enough. And so we can find the rise over the run of those. And the rise is, like it said here, g of a minus g of 0, and the run is a minus 0. And if we plug that in, we get a squared plus 3a plus 1 minus 0 squared plus 3 times 0 plus 1 over a minus 0. Right? That's exactly what that expression for the rise of the run is going to be. And then it's just a matter of simplifying. So you get a squared plus 3a plus 1 minus 1 over a, and that's a squared plus 3a over a. We can factor out an a out of the top, and then the magic things that happens in almost all of these types of situations where we've got a rise or a run expression is the a's cancel out, the denominator cancels out, and so we end up with just a little formula that is a plus 3. And so then that gives us the slope between the point at 0 and the point at a, and it's a plus 3. Well, let me show you the picture. So now if we look at the graph of x squared plus 3x plus 1 that we were trying, and we were looking at what happens when one value is at 0 and the other is at a. So we were looking at what happens when one of the values is 0 and the other one is close by. And we claimed that as this one gets, as the other point zooms in close, the slopes get closer and closer to 3. And you can check, it's 3.087. 3.3 plus the distance between the 2 points, 3 plus 0.087, which matches the formula we had before, a plus 3. some of these functions.